1 month to go. 1 month to go. How many people are graduating? 1 month to go. Actually, all of us 1 month to go. All right, so we'll push through. Push through. Almost there. Okay, because I know a lot of midterms are going on and very soon. All right, so date of the exams for 15. We pushed it because we wanted to do one more homework. The homework will be on Blackboard by tomorrow morning at the latest. It might be there by tonight. It'll be really good practice. So it's all designed to get you ready for the exam. Okay, so we're talking about molecular recognition, or you can think of it in another kind of simple way as just binding. This will apply to lots of different types of problems. Ultimately, we're going to think of it as non-covalent complexes, meaning that it's a real reversible equilibrium. Clearly, there's some irreversible stuff that's important too. A lot of new drugs are designed to be irreversibly inhibit particular targets. Those are important too. But for equilibria, we're going to deal with non-covalent complexes and learn how to calculate it. Like we said last class, there's this often this trade-off in biochemistry from having a certain affinity and specificity. Both of those, if you think about pharmacology, are absolutely critical. How well a drug binds its native target. And then obviously, this specificity term would be important if you had toxicity problems. If you design a drug and it's a great inhibitor of your target, it binds everything else in the cell, that's really, really important. That's a huge problem, a really huge problem. And so we need to understand both. So we're going to talk about affinity today. In latter classes, we'll talk about specificity terms. We'll touch on it a little bit. But we'll calculate those terms in later classes. For the purposes of your midterm, I care about affinity. I'll tell you exactly where the cutoff is, so you know. All right, so again, lots of systems we could think about it. The pharmacology is, the pharmacology issue is one where we really need to do binding equilibria. One really interesting one is transcription factors and how they bind their cognate DNA and turn DNA on and off. Obviously, they're critical for just about every physiological process. So it's really hard if you think about it, because there's a lot of DNA in a cell. There's a ton of sequence, right? There's millions of base pairs, and yet transcription factors have to find exactly the right target with high affinity, typically, to be able to do what they have to do. So it's an interesting problem. Okay, so here's the drug enzyme example. Obviously, affinity is a major term here. If I have a drug with really weak affinity for its target, it's pretty useless. So it has to be tight, it has to be specific. We'll need to understand the molecular basis of it. And ultimately, budding physicians in the audience, a couple, you need, or people that want to go to pharmacy school or whatever else, right? This is important, right? You prescribe a medicine, you give it a dosage. Okay, well, what dictates the dosage that needs to be effective? And ultimately, it's the equilibrium. And then there's this issue of drug-drug interactions. I'll show you in a second. Okay, so again, lots of issues of affinity and selectivity. Here's an antibody binding an antigen, and I would guess that this affinity is very good or very poor. Antibody antigen. Pretty darn good. If I were to put that KD in concentration terms, where would we guess they are? Millimolar or nanomolar? Nanomolar or better, right? So really, really not only high affinity interactions, but very often very specific interactions, right? So immunology dictates that it has to be that. Okay, so if I think of simple equilibria as biochemists, I think of things as a dissociation constant. As chemists, very often they define things as an association constant. It really just describes which point of the arrows you're really interested in. We're going to do KD. KD puts everything in concentration terms. That's handy for me because it tells me some idea of how well that ligand binds its specified target. All right, so we can also think about a delta G associated with any of these binding equilibria, and that's pretty easy to figure out based on all the equilibria we did. So again, it looks a lot like the histidine pKa equation, where we can very easily relate that equilibrium constant to a delta G of reaction. Okay, so these things could be more complex. We could have, here's an issue where we might have some drug-drug interaction. So basically we have sequential or coordinated binding of two things to the same protein or same enzyme. This is important. This provides this kind of two equilibria constant, one for binding of the first molecule and then one for binding of the second. In this particular case, I've not drawn it as any kind of cooperative interaction, but certainly, you've seen reversible binding of oxygen to hemoglobin and these sort of sigmoidal curves. And those are kind of this issue of cooperativity. Binding of the first may hurt or help binding of the second one. So as a pharmacology issue, this is really important. There's cooperativity. So we're first going to deal with non-cooperative systems. Ultimately, we'll touch a little bit on cooperative systems as well. All right, so I can relate everything to free energy of binding. I can think of the equilibria that way, meaning that my protein by itself will have some standard free energy. In this case, maybe I can normalize it to 0. My ligand that's going to bind the protein also has its own free energy of standard solution. And then, if I make a complex, it's going to have ultimately a lower free energy. Okay, so the lower that free energy is, the better the KD is, meaning numerically, the smaller the value of the KD. So, and I could think of it this way, right? Like ultimately the delta G is just RT ln of my dissociation constant. The smaller that KD is, the closer it is to 0. What is that going to be for my free energy? It's going to be lower, and it's going to be more and more and more negative. So all these numbers will typically be negative, but it'll be more negative the smaller my dissociation constant is, because once I take the ln of it. Okay, so intuitively it makes sense. Okay, so this ultimately we're going to sit on the right side, right, where we just do everything in terms of dissociation constant. If you did, so the only thing to really note here, right, is everything is plus RT ln of KD. And so it's really easy. All I have to do is know a KD, and I can figure out what that delta G of binding is, just like any other time. So biologically important interactions can be picomolar, can be femtomolar, can be really, really low for some interactions. We'll talk about the structural and functional basis of that. A particularly poor drug, or a situation where we have just a ton of ligand in the cell might have specifically weaker interactions. So it's really important to start gauging, all right, well, what is the ligand concentration in the environment that I'm interested in, to what the affinity is, because that will really dictate it. So it will make some amount of sense, and hopefully we'll have a couple examples just to illustrate that. All right, so the weaker my interaction is, the higher my delta G of binding. Meaning that if I have a millimolar type interaction, and this all just comes from this equation, the weaker my interaction is, millimolar in this case, I see, okay, well, I'm about minus 20 kilojoules per mole. If I tighten that interaction, if I go to the femtomolar, my delta G of binding is much, much more favorable and gets to, approaching minus 100 kilojoules per mole. So, there's a huge range that you could encounter. If I want to develop a drug, right, I want to be nanomolar, something less. That would be useful, because I really don't want to take 20 grams of the drug to make it effective. That would also cause a lot of other problems. Okay, so the meaning of KD. When we think of a KD, we're interested in the concentration of free ligand where and so I'm going to emphasize this point now, but we'll talk about exactly where this is coming from later. Basically, a concentration of free ligand where half of the protein molecules, I'm just going to do it in protein world, but it could be DNA, but half of them are bound to ligand. Okay, so that's what defines it. So we're going to define this, we've defined this parameter F, that basically is called fractional saturation. All right, so what is fractional saturation? All right, well, that's just some concentration of protein with the ligand bound over some total protein concentration. So this number is going to go from 0 to 1. I may express it sometimes in percentages, but you can easily go to a fraction from that. Okay, so this issue of KD, and so we looked at how to derive it. We looked at how to derive it last class. But now, where does this sort of meaning of KD come from? All right, so you can think about it this way. All right, so the fundamental equation that we're really interested in, if we have some fraction bound, that's just free ligand over ligand plus the dissociation constant. And ultimately, when we start plotting this stuff out, right, unless I do some permutation, right, I might have some fractional saturation, and this is my free ligand. And so these are a typical binding isotherm. So in the past, you looked at binding of oxygen to hemoglobin in a similar type graph like this? Okay, so what does hemoglobin look like? Does it look like this? It kind of does this like this S shape. Why does it do the S shape? Because you've got that cooperative binding phenomenon. All right, we'll talk about it later. But typically, one binding site will look something like that. That's a typical isotherm. All right, so this meaning of KD. All right, so let's just, for fun, right? Let's put our ligand concentration right at the KD. So this ultimately is the definition of where this KD comes from. Okay, so if I do that, and I put it into my fractional saturation equation, and I just substitute it, right? I get KD over KD plus KD. All right, so what's my fractional saturation? Just simply 1/2. Okay, so this is what defines where my KD is. So when we look at these plots, this will be approaching 1. Let's just say it starts at 0. Basically, I'll be looking at where it's 0.5 and go down. That's the constant, that's my KD. So there'll be lots and lots of methods to measure it, but ultimately that's what we're doing. Just measuring these, where it's half fractionally saturated. All right, so here's an example. It won't always be fractional saturation on the y-axis, right? It'll just be any kind of response that we're interested in. It will scale. This could be, we'll talk about some of the methods. It could be radioactivity, it could be fluorescence, it could be what have you. But what you're looking for is basically, if I keep going on and on, where I would basically max out, and that should be, that should be fully bound. If I just keep going, ligand concentration to infinity across the street. In this particular case, that's around 200. So then I look for, okay, well, where is it half that value? Here's 100. I go down. And this should be the ligand concentration that ultimately should correspond to my KD. So in this particular case, numerically, what's the KD around? I know it doesn't have units. But in terms of a number, what would it be? Five-ish, somewhere around there. This would be 10, so maybe around 5. All right, so lots of techniques in which we can measure this. Anything that was specific to pro-binding would be great. All right, so here's the ultimate definition. All right, so here's my protein in solution. Obviously, if I'm well lower than the dissociation constant in terms of my ligand concentration, none of my protein will be bound. If I go to infinity right across the street, everything is going to be saturated. Basically, my F is going to be equal to 1.
The critical thing is where things are half bound, I guess I could count the red blobs and how many have little green ligand blobs associated with them, but that should be 50-50 in terms of numeric value. That's my dissociation cost. All right, so it's a useful term because it defines 50% fractional bonding. All right, so how do we do it experimentally? I could throw lots of different methods at you. Ultimately, the only thing we need is some kind of response upon binding. All right, so technically what could I use? I could use some optical probe, if that were possible, if the color of something changed. I'll show you an example of that from stuff that we do in our lab. Fluorescence is a really good one. Any other spectroscopy you could think of that's specific for binding and can somehow tease out what is bound and what isn't bound. NMR, all kinds of things. Radioactivity is one that we'll touch on today. And then ultimately, a really, really good one is calorimetry that will measure heat absorbed or heat released on that binding event. So anytime something changes upon binding or dissociation, that's a really good probe. Ultimately, anything we can measure as a function of ligand concentration will be great. As long as it's specific, and as long as we can measure it accurately, it'll work. All right, and then some caveat, technique I'm going to choose is just going to depend on the system. But you can see all kinds of things. Ultimately, we're just looking at some change. All right, so here's an example from the textbook. This is an example of a steroid hormone binding a steroid hormone receptor, making a complex. That complex now is responsible for binding to DNA and then stimulating some transcription of some gene. So we could understand it at that level, we could understand it at the molecular level. Really, we're interested in two different binding events in this example. We're interested in the binding of the steroid hormone to the receptor, and then obviously we're interested in the receptor actually stimulating some DNA response, either through direct interaction or through some downstream interaction. So this is a really common biochemical one, right? Kinase type interactions are exactly like that. All right, so using that example, we can think of, okay, well, I'm really interested in how the steroid hormone binds the receptor, and so I needed to develop a probe. Okay, so the easiest way, well, one way, not necessarily easiest, but one way we could think about doing is just saying, okay, well, let's take the hormone and let's just tritiate a couple positions. All right, so the tritiated positions are H asterisks. All right, so that basically makes them radioactive, which is useful. What is good about using radioactivity in terms of a binding measurement? Why would radioactivity be a good probe? Or why would it be a bad one? Thinking about it the other way. Yeah, exactly. Okay, so that's bad. That's potentially bad. I don't want radioactivity in my lab. Okay, problem. You can get around it. Have nice shields. But it's not my method of choice because I don't like radioactivity in my lab. There's a lot of regulations involved in it. So that's a downside. What's a plus side? It's easy to distinguish and it's really easy to measure, and it's a really sensitive measure. Really sensitive ways to measure radioactivity, which is really helpful. So that might be a strength. I don't need much. I need very little concentration in order to do it. I also don't necessarily need any specific spectroscopic response to the protein. All I have to do is look for radioactivity. So the only thing I need to do is be able to separate the protein in some kind of way. All right, so it's useful. All right, so here is ultimately the experiment. I'm going to take the estrogen receptor that I'm really interested in. I'm going to take a solution of estrogen. Some of it is going to be spiked for radioactivity, in this case tritium. And then I'm going to mix this with some resin that specifically binds the receptor protein. It doesn't bind just the one bound to the ligand, it just binds all the receptor protein. All right, so once I do that, I could spin it down. So basically what that will do, the resin is really heavy, so I can easily centrifuge that down. What should be remaining in solution is just all the unbound estrogen.
what should be remaining down at the bottom is specifically my receptor. I could put this in my favorite way to measure radioactivity. Let's call it assimilation counter. And I basically could, measure the number of counts and say, okay, well, I can relate that to how much ligand is bound to the receptor. So relatively an easy experiment. All right, so the purpose of the resin in this case is really to make this thing a molecular match and to separate out all the protein from free ligand. So what that means is I'm specifically getting a readout, at least thinking about it in terms of an equilibrium constant, I'm getting a specific readout of my protein ligand complex or that concentration, which I can simply relate to radioactivity. If some of the free ligand, so we have to kind of also consider the potential pitfalls. If some of this protein doesn't bind the resin, is that okay, or would that lead to false measurements? If some of my free ligand binds the resin directly, that's also problematic, because this no longer becomes a really good readout, a specific readout of my protein ligand complex. Let's just say that the spike estrogen binds the resin all over the place. It will look like a lot of ligand is bound to the protein, even though it's not. It's just bound not specifically to the resin. So those are particular things that we could worry about. I can measure radioactivity, and ultimately I could get some gauge of my protein. So that's ultimately how the experiment would work. All right, so why use the resin? Well, the resin's really good. Use it in DNA all the time. You can use things like nitrocellulose. In this case, I'm just pouring that cocktail across the filter, and then just saying, okay, well, all the free ligand stuff goes through because it's small molecular weight. All of the protein stays on top because there's an interaction with the nitrocellulose filters. So it might be a good way to trap protein and trap protein ligand complex, all protein, but we're interested in protein ligand complexes, whereas all the estrogen, unbound estrogen just goes through. So centrifugation format, pour over filter format, but essentially they're doing the same thing. All right, so measure radioactivity, and that's okay. So a little bit about the details of this experiment. So nitrocellulose, the structure looks, at least the unit of the polymer looks something like this. All right, so why would this be good for binding proteins? Just let's look at the charge properties. You see charges on nitrocellulose? I see a lot of charges on nitrocellulose. So would it be good for binding to the exterior proteins? Probably, right? Lots of polar groups on a protein would be really good. How about nucleic acids? Would this be good for binding nucleic acids? Also probably pretty good. There's a lot of charge, a lot of positive charge. So people also use nitrocellulose for doing DNA. So good generic filter for binding charged molecules. If I look at the free ligand itself, should that nitrocellulose bind the free ligand?
Yeah.
Is the free ligand charged? I don't see any charges on the free ligand, so hopefully it wouldn't bind the filter. If all things go well. All right, so a little bit about radioactivity. I'm not going to go into the whole radiation physics of it, but beta emitters like carbon-14 are really good. What defines a good emitter, right, is some neutron-rich nucleus. And the only reason I want to relate this to something that we learned about, but during this radioactive decay process, the neutron basically ejects some electron in the form of a beta particle and an antineutrino, and ultimately that's going to form a photon. All right, that's the radiation physics of it. The general equation is something like this. You will have probably seen radioactive decay at some point. Here's a generic carbon-14 which ultimately through beta decay is going to make nitrogen 14. All right, so here's the critical thing, right? The neutron is going to turn into a proton, electron, anti-neutrino. That's fine, but here's a typical energy curve for something like beta emission. All right, so here is a number. So here's the critical thing. I'm going to distribute the energy that comes off from beta emission in terms of this beta particle and the neutrino. All right, so what does that mean? That means that every radioisotope has an energy spectrum like this, meaning that I'll have a distribution of beta particles of a certain energy that will max at some specific point. The nice thing about radioactivity is I can make it selective. So any kind of beta emitter would have a different max energy and a different distribution. And I can actually get instrumentation that could filter one energy versus the other. Now, here's relating back to something we learned. You see that it has a distribution. All right, if I go out here, really high energy, why are there no particles? Or at least a small number of particles. What dictates that? It does relate to something you learned. I know it's a completely different phenomenon. All right, so it's a distribution. It's a distribution with some difference in energy. What determines probability as a function of energy difference? Someone said it. Starts with a B. Boltzmann. All right, so here's another real-life example of the Boltzmann. Distributions like this will be guided by the Boltzmann. It depends on the energy difference, and that will govern populations. So in this particular case, it's beta emission. It has nothing to do with probabilities that you've seen in energy. Well, it does. It's basically energy levels and looking at distributions and looking at probabilities. So that's the reason I show you this beta emission process. Okay. So we do this experiment. Basically, we were just going to do radioactive counts. And in this case, it goes from 0 and maxes out about 200. I plot this as a concentration of free ligand. This might be in nanomolar. So if this saturates around 200, I'm looking for the 100 point. I go across, I go down, and I get my KD. Hopefully I get my KD as long as I've done the experiment really well. And my KD will be about 5 nanomolar. All right, so questions in this. Do we need to know how much receptor we've used in the experiment? Do we know from this? Not necessarily. We do need to know that what the free ligand concentration is, clearly, when we're doing the titration and collecting all these points. But if we do this really well, we should be able to determine the dissociation constant. So it's easy enough experiment as long as you're bold enough to use radioactivity. All right, so if we can do some kind of special things with it, meaning that we can plot these things in different ways. So the standard way is something like this, where I have a concentration and I have some spectroscopic response on the y-axis, but it's not the only way to do it. I can certainly fit this equation to that binding isotope. All right, but there are also kind of other ways to do this experiment. So if I want, I can also think about the fraction of the protein rather than that's bound. I can think of the fraction that isn't bound also. All right, so if I do that, basically what I'm interested in is just, instead of F, I'm interested in 1 minus F. All right, glass half empty instead of glass half full. All right, so here is 1 minus F. Simply what I took was the definition of F, which is just ligand over ligand plus KD. I've just taken 1 minus F. Okay, so then the next step is I can just make 1 equal to ligand plus KD over ligand plus KD, which will basically just put my whole denominator in terms of ligand plus KD. That helps me collapse things in terms of this term. My ligands all kind of cancel out at this point, just become equal to 0, and I get something like this. All right, so again, this is just thinking about what isn't bound rather than what's bound. Just a simple permutation of it. All right, so why is that helpful? It's helpful because if I have methods that can distinguish between fraction bound and fraction unbound, I can just take my formal definitions of it, and this just collapses into something very simple, and ultimately what I get is just ligand over KD. All right, so if I have a way to distinguish bound and unbound, I can take that ratio, and that'll just equal to ligand over KD, which is really helpful. All right, so if I think of taking the log of this, so in other words, if I'm interested in just taking the log of my fraction bound over my fraction unbound, it would look something like this. I said, okay, well, this numerically, fraction bound over unbound, is simply ligand over KD. So I'm going to take the log of that too. Log of ligand over dissociation. All right, so I can work through that, right? That's just simply equal to my log of ligand minus my log of dissociation constant. All right, so why is that helpful? If I plot that, if I plot a log-log plot, where I have fraction bound over 1 minus fraction, and I plot that versus log L, what should I get? I should hopefully get a line. Okay, so if I don't want to use the kind of normal equations, this is really simple because this should give me a line. All right, so here's the normal one. Here's just plotting F versus some concentration of ligand. I see the normal kind of isotherm, right? Kind of hyperbolic plot. If I go into log-log, log of F over 1 minus F versus log of L. We see now that it goes and just forms a straight line. Easy to fit. You could fit both, but sometimes we like straight lines to fit. It's easy. All right, so in this, where is my KD at? What's my fraction bound at my KD? What's F equal to?
1/2.
1/2. All right, what's my fraction unbound?
1/2.
1/2. All right, so what's log F over 1 minus F at the KD? 1/2 over 1/2 is equal to what? 1. What's log of 1?
0.
All right, cool. 0. Here's my KD. So I could show you a plot like this, right? A log-log plot, and that's how I would experimentally determine my KD. All right, so notice that there's some, for analytical chemists, there's a strange, here are the error bars. Where were the error bars? Here are the error bars for the measurement. All right, so you see something kind of symptomatic, right? What happens to the error? Why are some measurements really good and some aren't? Well, first, is there a dependence on it? So when it's highly negative, you see the error will go up. Absolutely. All right, so what concentrations are those? They're really low. All right, so why is the error so much poorer at low concentrations?
well below the KD. How much protein is in the protein ligand complex at low concentrations? Alright, I'll put it another way. What's my fractional saturation at low concentrations of ligand? Low or high? Low, because I barely added any ligands and most of my protein is free. Alright, so if I am measuring radioactivity of my protein ligand complex, specifically, what do you expect? Lots of radioactivity or very little? Very, very little. Okay, if I'm measuring something little, my error is going to go up. So that's pretty typical. Very small spectroscopic response that I'm measuring, right? There's going to be a lot of error associated with that measurement. As I go higher and higher, you see that the error bars are getting cleaner and cleaner and cleaner. So high reproducibility of that measurement, low error. So that's all that means. So this is pretty typical. You might expect to see that in terms of error properties. All right, so hyperbolic plots kind of rule, right? If I don't do a log-log plot, something might look, I might have some curve that looks like this. So this was an example from the back of the text, right? So shown below is binding isotherm for. Now, here's the critical thing. These questions will have a lot of verbiage to them. So you have to decide what you need and don't need from these questions. I throw in a lot of kind of real-world examples, which I find interesting, more interesting than just kind of a generic plot. But with that said, there's a lot of things you don't need to know. All right, so here's an example. Shown below is some binding isotherm for a phosphatase and a lead compound. We'll talk about lead compounds in drug design, but basically sometimes those are the precursor compounds that people are deciding, is that a good drug? Is that a really junky drug? Should I pursue it? Should I make modifications to it, do a lot of organic synthesis, or should I just throw it away? This is a particularly good one. All right, so that's the detail. There's a tryptophan near the binding site. Tryptophans fluoresce, by the way, and they're very environmentally sensitive in terms of fluorescence. But that tryptophan will increase fluorescence when the compound binds. All right, so the plot looks something like this. Here's JF99, here's titrating my drug, here's my fluorescence response. So it's not radioactivity anymore, I'm using a different technique to measure it. All right, so here's the binding curve. And what it says is, okay, well, at the highest concentration of JF99 tested, which is 1 micromolar. Notice that this is a nanomolar, so what that means is 1 micromolar is probably across the room. But at its max, it's about 490 units. All right, what's the KD? What do we think? What's the dissociation constant? 15 nanomolar. Okay, so how do we do it? Okay, so 490 is the max. So 490 is across the room. Everything is bound at that point. So what I do is I just take 490 divided by 2. That's the spectroscopic response I'm interested in. That's roughly 245, 250, right? 250 across, 250 down.